The energy balance is one of the fundamental laws of physics, and we use it all the time in our chemical engineering problem solving. So I'd like to do an example of a steady state macroscopic energy balance. And the one I've chosen is heating a flowing liquid stream. So here's the problem statement. Water enters the inside of a double pipe heat exchanger and flows at 3.4 gallons per minute. The inlet water temperature is given, the outlet water temperature is given. How much heat does it take to feed the stream? So as always, we'll begin with sketching the problem. So let's do it. So it's a double pipe heat exchanger, but fundamentally we just have something that's going to heat this water stream. So in comes the water stream at 3.5 gallons per minute, 3.4 gallons per minute, water, liquid, 3.4 gallons per minute, water, liquid. And it comes in at 17.0 degrees C. It comes out at 42.3 degrees C. Some kind of a device puts heat into the stream in order for it to come out hotter. So this is going to be an open system balance. So the open system balance is appropriate when you have a system that mass crosses the boundaries, as it does in this heater. This heater is the double pipe heat exchanger. So in an introductory chemical engineering course, we teach you about energy balances. And I want to share with you a summary of the energy balances that I have posted on the internet. Here's the link down here at the bottom. And this allows us to look at a very large scale at the choices of balances that we use. I know how to do this problem, so I could just go right to the answer, but if you're watching this video, maybe you don't know off the top of your head how to do this problem, and so you have to decide. So we're going to decide between the open system balance, the closed system balance, and the mechanical energy balance. And the mechanical energy balance is not applicable when heat is transferred, so that's not correct. It's not a closed system because mass does cross the boundaries being around the heater. And so we're going to use the open system. So we're going to use the macroscopic open system energy balance. Sometimes this is written as heat balance, but heat doesn't balance energy balances. And this is, we can copy it from the sheet. It's delta energy potential plus delta energy kinetic plus delta H. Delta H is present in the open system balance, equals the heat in plus the work shaft on. So now we need to simplify this. And potential energy is asking whether this stream goes through some sort of lifting in a gravity field, gets higher or lower. That's negligible. The kinetic energy term asks, is the speed of the flow important to the energy exchanges? And it is not, because it's simply coming through at a modest speed. And the biggest thing that's happening is the heating. So the enthalpy change is asking, are there any changes in internal energy, which includes temperature and pressure? And there certainly are changes in temperature, so between the two streams. So we keep it. Heat, there's definitely heat in. If there are no shafts, there's no shaft work. So the thing we're looking for, Q in, is just equal to delta H. And then we have to go back, and it's on the summary sheet, or you can go back to the reference that you used when you learned about open system balances. This is equal to the sum of the outs minus the sum of the ins of m sub I, h sub I. So this is the specific enthalpy and the mass flow rate, m sub j, h sub j. So this is the summation over the I, summation over the j's. So now we apply this to our case. We have one outlet stream, one inlet stream, and the mass flow rate is the same throughout. And so we can pull the mass out and go enthalpy out minus enthalpy in is equal to the Q in that we're looking for. So this is the equation that we need to evaluate. And we can go one step farther by looking at how do we calculate an enthalpy change in a stream that is a liquid. So this is a liquid in both cases. And again, if we go back to Felder and Rousseau, which is the book I use, or to whatever text we use to learn our fundamentals of how energy is moved around in a stream, we can find how enthalpy changes are calculated in a liquid when it goes with temperature only changing. So those are the specifics that we have to keep track of and know to choose the correct step at the next point here. So the enthalpy change for a liquid, we're constant pressure with only the temperature changes given by Cp delta T. So Q in is equal to M, and then this delta H is going to be the heat capacity of the water times T out minus T in. So this is now an equation we can evaluate directly. We need the mass flow rate of the water, which we need to get from the gallons per minute, 3.4 gallons per minute. We need the heat capacity of water, and we need the temperature out, which we know is 42.3. The temperature in is 17. So those are good. We need to evaluate these other two, and we're ready to go. So the other useful sheet that I like to have around when I'm doing this kind of calculation is to have the this sheet of unit conversions. It's also available online, and I encourage you to download it and make use of it. So here's the URL for getting a copy for yourself of the unit conversion sheet. And because we deal with water so often, it has the heat capacity of water here on the back. So I'm just going to copy down the heat capacity of water. So the heat capacity of water is 4.182 kilojoules per kilogram Kelvin. And now we need the mass flow rate and then do some unit conversions. So the rest of the unit conversions we can also find on this sheet and carry out the rest of the calculations, which I can leave to you. So I can put into the notes on the video the answer to the question that we finally calculate, and then we're done. So just to recap, the question was, what is the heat input into the water stream to get it to go from 17 to 42.3? And our solution was to sketch, then identify which piece of physics would constrain the system and allow us to calculate the answer. And it's the macroscopic open system energy balance. Then we need to know simplification steps for this problem. No potential, no kinetic energy changes. That will be the case when we have simple heaters. No shafts, no shaft work. Understanding what the delta means, and also how to calculate enthalpy changes for various situations. And so for a liquid, isobarically changing only temperature, it's Cp delta T out minus in, and onward to get our final answer.